Now let's talk about linear regression in a setting where it's a bit more concrete, where we have a prediction, a more clear question. So here our question is just for a given person, so I have this data set. Yeah, so you can get it from here. It's this ABM data. I think it's called ABM, and if you want to play with it, you have to download the newer version of the medical data package, this is how you do it. But anyways, so in this data set, we have the outcome is whether or not people have this bacterial meningitis infection, which it's hard to tell in practice when people come in if they have this or if there's just some other thing going on. And so you might be interested in building a model which says, okay, given some predictors, in this case, using this person's sex, age, and this blood glucose measurement when they show up in the ER. Can I predict if they have this infection, and maybe if they have a high predicted risk of this infection, that we're going to treat them differently, right? So this would be a nice thing to have. And we can do this with logistic regression. So we can fit this logistic regression model, and then let's say somebody walks into the clinic, and sex is coded as 1, which is a female, age is 55, and the blood glucose is 101. We can just generate the prediction on this new data, and here it says 15. It's about 15%. So this person is, a relatively, maybe that's a relatively low risk, and so we're not gonna, rush them into treatment. We're just gonna do the normal stuff for this person. But for somebody else who had different values, it might be a high predicted chance, and so we would do something different, right? Question is, how accurate are the predictions? So if our question, if our goal is just to make a model that can predict accurately, what we need to know is how accurate are those predictions really. So we need a way of judging our predicted probability of the outcome relative to the actual outcome. And there's many different evaluation metrics. Again, this parallels the case with linear regression, where we ended up using MSE for most things. But here it's actually a little bit more complicated because I can directly compare this predicted probability to the outcome and say, okay, my model gets more points when if the outcome is something that actually happened, then I want my predicted probability to be higher, and that'll give me more points. And so that's like basically the cross entropy loss that we came up. That's one way to do it, or squared error loss. That's fine. You're directly comparing the predicted probability to the outcome. The other option is say, okay, I'm not going to. Ultimately, what I'm doing, if I see a predicted probability of 15%, that doesn't really matter what that actual number that's coming out is, because the way that I'm going to use it is just say if it's over a particular threshold, I'm going to act one way. So if this is over 60%, I'm going to rush this person to the ER or whatever. And if it's lower than 60%, I'm just going to let them wait in the waiting room. And so it really just matters whether or not the prediction is over that threshold or under that threshold. So I could alternatively pick a cutoff for P and then compare the outcome, which is 0, 1, to the predicted outcome. So if P is greater than 60%, I'm going to say I'm predicting the outcome is 1. If it's lower, I'm going to predict the outcome is 0. And this is a different set of metrics. So no matter what you end up doing, you do want to use a test set like we talked about last time. You want out-of-sample validation of what's going on. And so the general setup will be something like this. So here I have this data set, and I have my outcome. This is a different data set. The outcome here is remission. I first split the data. So this comes from the tidy models package. And then I train the model to predict the outcome based on everything, in this case, everything else that's in this data set, using the training data. And then for the testing data, I generate the predictions, and then I can compare the outcome and the predicted probability. So this is what that's going to look like. So this is on test data. So these are outcomes that the model has never seen before, and this is the predictions. So you can see, for example, here, this person who's didn't end up having the outcome, the model is predicting a pretty low chance, only 30%. Same with here. And then for the people who have the outcome, you see some pretty high probabilities. But it's not perfect, right? There's people for whom they had the outcome. Okay, so here's somebody who had the outcome, and the model's predicting a low probability, lower than this person who didn't have the outcome. So how do you judge whether this is a good model or a bad model? So one way, like we talked about, we can just use cross entropy. And I can implement that like that, and here's the number that I get back. Okay, that's fine. This number doesn't have a pretty strong inherent meaning by itself, I think. It's not that interpretable. But what you can use this for is to compare two models. So if you compare two models, whichever one has the lower cross entropy is, generally what you can say is that the predicted probabilities are somehow closer, better predictors of the true outcome than for the model that has higher cross entropy. And so oftentimes for these kinds of models, what people are doing is instead looking at these metrics where you've binarized the predicted probability. So here, for example, I'm looking, is the predicted probability greater than 0.5? And if it is, then I'm going to say this person is a predicted outcome. And if not, I'm going to say they're predicted not to have the outcome. So you're first doing this mutate, and then you're judging based on that. So here, what I'm calculating is what's called accuracy, which is just when did my prediction agree with what actually happened. So if the person actually had the outcome and I predict the outcome, I get 1 point. If the person didn't have the outcome and I predicted them not to have the outcome, I get 1 point. If the prediction is different than the actual outcome, I get no points for that. And then I'm just tallying up how many total points did I get out of all the possible pairs. And here I get 68% accuracy. That's very interpretable. How many times do I predict the correct outcome? So there's actually a lot of these metrics that people use. Accuracy is one of them. There's a lot of related metrics. Once you've binarized the predicted probability, there are many metrics that you can use that all rely on these 2x2 tables. You've probably seen these before. So you can make a table and say how many people that didn't have the outcome, I predicted them not to have the outcome. How many didn't have the outcome did I predict to have the outcome, and so on and so forth. And so you make this table, and now we can compute several different metrics. So accuracy is one of them. We already talked about that. When is my prediction the same as the observed value? And that's equivalent to summing up these numbers on the diagonal, which are the correct predictions, and dividing them by the total of all of these numbers. That's called accuracy. There's also true positive rate, which is also called sensitivity or recall. And that is, out of everyone who did have the outcome, how many of those did I catch? So that here, this is looking pretty good, right? We're catching somewhere around 500 out of 700 of the outcomes. You might also ask, out of the people who I predicted to have the outcome, how many of those actually did have the outcome? And that's this number divided by the total of these two. That's called positive predictive value, or also precision. And another number that people calculate is something called specificity, or true negative rate, which is out of the people who did not have the outcome, how many of them did I predict to actually not have the outcome? So these are all different metrics, and they measure different things. So the thing to know is that you should be measuring your model's performance in a way that makes sense to your problem, right? There's none of these metrics is right or wrong. They're just measuring different aspects of the predictive capability of the model. So, for example, for true positive rate, this one here, right? You're measuring how many out of all the people who did have the outcome, how many of them did I catch? So that one makes sense when what you're trying to do is catch as many cases as possible, and you don't care too much about false positives because that for whatever reason, maybe if whatever intervention that you're going to do is very cheap and it's effective, and you don't mind giving it to people who weren't actually going to have the outcome. You just want to catch as many of the people who were going to have the outcome, because that's what's really expensive or harmful, is having people have the outcome that you didn't predict. On the other hand, positive predictive value, this one here, your denominator is the number of people that you're predicting positive, and your numerator is how many of those actually had the outcome. And there you might want that to be high if you want every case that you flag to be a true positive, but you don't really care about missing cases. So this positive predictive value, notice, it doesn't care about this number, which is the number of people who have the outcome, but you don't predict them to have the outcome. So if you don't care about that, you don't care about you're missing these cases. You just want to make sure that every person that you flag is actually somebody who you needed to treat. Then that makes sense. So for example, like let's say you have an intervention that's super, super expensive. Maybe it has some side effects. You don't really want to deploy this super widely. You just want to make sure that whoever is getting it is somebody who's actually going to be benefiting from it, right? Well, then something like positive predictive value or precision is a more sensible metric to be using. So you have to actually think about your problem. And you can, of course, weight combinations of these things. You have to think about this. This is not a statistics question. This is a domain expertise question. What are we trying to do with this predictive model? What are we going to use these predictions for? And that should be determining how we judge what is good in terms of prediction. Now, one problem with these metrics, these 2x2 table metrics, is that they vary with the threshold that you pick. So here, for example, I was using p greater than 0.5 to say the outcome is predicted positive versus predicted negative. And if I had changed what this number is, then all of these numbers will change around. And so what I could do is I could make a plot of how the positive predictive value and the sensitivity, for example, change as I change this threshold, and see what happens. So here the sensitivity, as I change the threshold from 0 to 1, let's just look at this for a second, is increasing. So if sensitivity is, recall is called, the sensitivity is how many of the people who have the outcome, how many am I saying did actually have the outcome. So the reason this is going up as I increase my threshold is because when my threshold is 1, I'm saying I predict everyone to have the outcome, right? So at that point, when I'm predicting everyone has the outcome, I am catching all of the cases. Of course, I'm also catching all of the people who didn't have the outcome, but sensitivity doesn't care about that. I'm not measuring that with sensitivity. So you can get perfect sensitivity by just saying everyone gets the outcome, right? And the sensitivity is 0 if I'm saying nobody gets the outcome, because I'm not going to catch any of the cases. So great. That's how this curve changes. Now, positive predicted value is changing a little bit differently. So if I'm saying everybody gets the outcome, then so if I'm saying everyone gets the outcome, then everyone is predicted to have y hat be 1, and this is measuring out of the cases that you flag how many are 1. So this is going to approach whatever the population rate of the outcome actually is. So in this case, the population rate of the outcome is somewhere a little less than 50%, and that's what you're going to be what you're going to be catching here. But of course, if you say, okay, I'm going to be a little bit more discriminate with my threshold, and I'm going to say I'm only going to say they're positive if they have a very, very high, predicted probability, then I may get a better positive predictive value, because then the people who I'm flagging, I'm really just flagging those people who are at highest risk, okay? And that's going to make your PPV a bit better. So my point is just that these metrics vary with the threshold. The details are not super important. You can review that later, but you can use this to pick a threshold that gives you a good trade-off. If you're thinking about what metric should I use, you can always plot these two things and say, and then what threshold should I use in practice? You can kind of look at, okay, if I choose this threshold, I'm going to get this sensitivity and this positive predictive value. And based on your own judgment of what the trade-off is between a false positive result and a false negative result, then you can pick a threshold that is going to be useful in practice. There's also this other thing called area under the something curve. So for example, this is a AUP-RC, precision recall curve. So precision and sensitivity recall, same thing. Where you plot as you vary the threshold, you plot your precision against the sensitivity. So here I've just plotted the recall and precision and the threshold, right? So if I just plot this versus this, you get a plot that looks like this. And then you can take the area under that, and that's kind of a way of averaging across the performance of all these different thresholds. And oftentimes you'll see this is what people report, either area under precision recall curve or area under the receiver operating curve, which is where you have sensitivity here and specificity here, which I don't think is as good as this in general. There's easy ways to generate all of these things in R with the tidy models package. So sometimes you see these things reported in papers as a measurement of how good the prediction is. This is fine. I mean, it's good for comparing models because now it's, again, threshold agnostic. But I think it loses its kind of clear interpretability. And I like it better when people actually think more clearly about their problem, what it is that they're trying to optimize, what's the trade-off between a false positive result and a true negative result and a true positive, and so on and so forth, and clearly argue for why it's this particular combination of sensitivity and precision and things like that. That is what it's the right thing to be doing for this problem. Once you start doing this, you start just being like a statistician and not really thinking about the domain, not really thinking about how this is going to be applied. And that's generally less good. Okay, so big picture, logistic regression and predictions. It's easy to use a logistic regression for prediction. You just run the model, you extract the predictions, you can use those. The question is, how good is that prediction? And to assess that prediction, you need to use a test set, which we talked about last time. And then you need to pick a metric, an evaluation metric that makes sense for your problem. And that choice is up to what the problem is. It's not a statistical choice. There's no right way to do it. You just have to think about, what do you want? What do you want this prediction? How is it going to be used? What do you want it to do? And the coefficients are completely irrelevant for this. They do not matter. You do not care what is going on inside the model. You can treat it as a totally black box thing. It doesn't matter why or how or what. The only thing that matters is what are the predictions and how good are they. So let's do a quick problem here. So let's use this data set. Okay, so we got the data. What are we trying to do here? Okay, we're using this thing to this data set to predict remission. How much does the test set AUPRC decrease or increase if we consider a model without this predictor? So let's just copy the code from here. Let's do, why not? So we got our data, split it up, run our model. Oh, we need this package. Great. So we got our predictions. And this is asking us to evaluate test set AUPRC. So it's area under the precision recall curve. That is this. So we should be able to do it like that if there's not weird stuff. Okay. So something that comes up if you're using these functions from the tidy models package, which is kind of annoying, is that this thing tidy models package wants everything to be, all the data to be factors, not binary. So here is remission. I think here we can just do as underscore factor. And then this should be okay. But now let's make sure. Okay, there we go. So this is a really annoying thing. If you don't know about factors in R, you can learn about them like that, or ChatGPT, but basically, tidy models needs to know which is considered to be outcome and which is not outcome. And the way it knows that is based on the levels of the factors. So you need to make sure that the orders are correct. So if I do as factor prediction y, you see the levels are 0 and 1, and they need to be, so tidy models is assuming that the 0 is the positive case and the 1 is the negative case, because they're in this order. So I need to manually set them to have this order. That's just an annoying thing. It really doesn't matter to the understanding that I'm trying to convey in the course. It's just a small coding detail, very annoying thing about this. But anyways, okay, so this is my test set AUC, PR AUC that I'm asking about. If I have a logistic regression model with everything, and now I say, okay, what if that logistic regression has everything except for this days of life predictor? So I can do it like this. Oops, that goes up here. Everything except for this this predictor. Let's see what happens if I train it. And I get the predictions, and now let's get this AUC. So the AUC, it decreased just a little bit, not a lot, but a little bit. So the conclusion there would be, is this, if somebody were asking, is this a useful predictor? I would say, based on this, if this is an appropriate metric to be using for this problem, which may or may not be true, but assuming that this is an appropriate metric, I would say that this predictor is not substantially useful. It's maybe a little bit useful, so it certainly is not hurting us, right? Like it does increase if we include it as a predictor. It does increase the predictive capacity of the model. But if this is a predictor that in practice would cost a lot of money to collect for new people coming into the clinic, it's not something that's already recorded. Is it worthwhile? Doing the expenditures necessary to collect that? Probably not. So this is how you would ask and answer those kinds of questions. All right, next one is, I have an intervention. I know it's effective in preventing remission for everyone, but it's really expensive and it has some really bad side effects. And I want to use a predictive model to assign this medication to high-risk patients. The question here is, what evaluation metric might make sense to compare if I had two different predictive models that are saying who is high risk and who's not high risk? What evaluation metric might make sense here? So in this case, I'd say something that is more heavily leaning on positive predictive value or precision is what's important, because I do not want to be prescribing this medication to people who are not actually high risk. So what I care about is just that the people who I'm predicting to be high risk are actually going to get the outcome. That's it. I don't care if there's people who get the outcome and I'm not catching them, or I care less about that, right? So maybe what I want to be doing here is have some weighted combination of precision, where I have a lot of weight on precision and maybe just a little bit on sensitivity. Or if I were looking at the curves like this, right? If this is my precision and this is my sensitivity curve, I'd maybe want to choose, if I were choosing a threshold, if I had a logistic regression model that I had built, and I just want to know where should I threshold, at what point should I start giving this thing out, I maybe want to choose somewhere around here, right? And yeah, that's very low sensitivity. If I'm thresholding based on 0.25 or something like that, then I'm not really catching a lot of the people who have the outcome. I'm only catching 25% of them. But I don't really care, because I know that at least for the people who I am flagging, they're really over 75% of them are actually going to go on to have the outcome. And so I might consider, well, maybe I want to catch a little bit more, but what's the trade-off? If I want to take it up to, I'm catching now 50%, my positive predictive value goes from like 75% to somewhere around, I don't know, let's say that's like a 63% or something like that. So you have to weigh whether that doubling the sensitivity is worth that decrease in precision. And maybe it is, maybe it's not. But if you really don't want to be giving this intervention to people who actually don't need it, even though that's a much smaller decrease in precision than the increase in sensitivity, it might still be worthwhile to not increase the threshold that much and maybe pick somewhere around here. All right, here's another question. Let's generate data using this data generating process. And let me just copy this into R so we can have it all in one place. So step 1, split this into training and test sets. Step 2, fit a logistic regression and a linear regression model. And then compute the test set cross-entropy loss for both models, which is better. And then plot predictions as well as the true conditional mean function and explain the result. So take a minute and try that by yourselves. So I've actually got code already down here. Okay, so first step, split the data. That's easy. We can use this initial split function, and I think the default is 80-20. Oh, it's actually 3/4, so we can use prop is equal to 4/5. Okay, and now we're going to fit two models. One is logistic regression, one is linear regression. So I told you that linear regression can give conditional mean functions that are outside of the bounds, but that doesn't mean that you can't fit a linear regression when the data are binary. Linear regression doesn't care. It'll just try to minimize, it'll just try to fit a line and minimize mean squared error. So you can do it. So here I've done, this is logistic regression. Here's linear regression. No problem. It runs, it's not like it breaks or anything. On the other hand, you can't do logistic regression in a problem with continuous data because that loss function for logistic regression is not defined for continuous data, so that won't work. But you can definitely do linear regression with binary outcomes, no problem. And now we're going to compute the test set cross entropy for both models. So here's for my logistic regression. What I'm going to do is get the predictions on the testing data. And then this is my my predicted probabilities. So to compute the cross entropy, I'm going to get the predicted probability of the outcome if the true outcome was y, and otherwise I'm going to get the predicted probability of not having the outcome. And then I'm going to take the log of those, take the mean, and then multiply by -1. So this is just implementing the cross entropy loss. So let's run it. So I get about 0.5. Let me make sure I ran these things. Okay. Okay, there we go. So yeah, that's for our logistic regression. And now for our linear regression, I get this. So what you notice is actually the cross entropy loss in this case for the linear regression is lower. It's better. If I'm measuring predictive accuracy with the cross entropy, I get better cross entropy with linear regression than I do with logistic regression, even though the linear regression isn't even trying to minimize cross entropy, it's trying to minimize the mean squared error, but I'm actually doing better. Interesting. So let's plot the predicted probabilities for both models. And this is what I see. So this is as I change the value of the predictor, how do the predicted probabilities change? And as should be kind of obvious, the linear regression model is predicting that the probabilities change linearly. The probability of the outcome changes linearly. And in this case, you see it's actually not predicting outside of the bounds. So great, maybe a little bit up here. And And the logistic regression has to fit this kind of S curve. And this is the curve that we're fitting. So they're a bit different. The question is, why is it that the linear regression model has lower cross entropy? Why is it that it's doing better? And for that, you can look at actually the original data generating process. What is the true probability of y equals 1 given x? Well, it's right here. It's just x. So the true probability of y equals 1 given x actually varies linearly with x, not in some logistic function. Okay? And what that means is that the logistic regression model is not going to be able to actually accurately capture the true relationship, which in this case is actually linear. And that's why it's actually giving you a slightly worse prediction. So if I were to plot here kind of truth, so here the truth is y equals x, right? Should be like this. Okay, so you see the black line, the gray line, they're almost on top of each other. So the linear regression is basically nailing it, while the logistic regression, it can't fit a straight line. It can only fit this S. And so the closest it can come is kind of making the curve pretty flat, right? This is just the best that it can do. It can actually fit a straight line like that. And what that means is that it doesn't do as good of a job of predicting in this particular case. Now, this is specific to the fact that we have this data generating process set up in this way where the true relationship is linear instead of being kind of a logistic function wrapped around a linear model. But hopefully what that should tell you is that there's nothing special about logistic regression, right? You don't have to see binary outcome and think, I have to do a logistic regression, see a continuous outcome, I have to do linear regression. Yeah, you can't do logistic regression when the outcome is linear, but both of them are just making a certain assumption about what the class of functions are that you're going to search. And if so you just have to think about it, is the true function more likely to be in this model class or in that model class? And it's perfectly reasonable to fit a linear regression if you want to predict binary data. It's, maybe a priori it makes a little less sense because your predictions could be greater than 0 or 1, but you could always just cap it. You could say if my linear regression prediction is greater than 1, I'm going to cap it at 0.95. And if it's less than 0, I'm going to cap it at 0.005 or something like that. That's totally fine. You can test that. You can see what the predictive accuracy is, and if it's worse, if it's better, you judge it purely empirically. There's no reason to let the data dictate the kind of functions that you're trying to fit necessarily, right? It doesn't have to be this S shape. There's no need for that as well. So I'm just trying to break out of the idea that like the kind of data should not always necessarily dictate the kind of model that you're going to use.